Welcome to The Explainer. Today we're going to unravel a really fascinating, real-world engineering mystery. So I want you to imagine you're sitting in a high-stakes technical interview, right? The interviewer leans in and asks, what do we use in an electrical panel to protect a motor from burning out? Now the standard, by-the-book answer is, of course, an overload relay. But then they hit you with a totally unexpected cross-question. It's the kind of question that forces you to throw the textbook out the window and look at what actually happens out there on the messy, unpredictable factory floor.
And here is that massive paradox. If pretty much every industrial panel out there has an overload relay installed, a device whose entire job is to stop a motor from burning out, why in the world do we still see fried burnout motors all the time? It makes no sense, right? It's literally where textbook theory collides head-on with practical reality. So let's play detective and explore exactly why this happens.
All right, let's dive into this. Suspect number 1, single phasing, the silent overheater.
Now, most heavy-duty industrial applications use what's called a three-phase induction motor. Basically, it relies on three distinct electrical phases pulling together to run smoothly. Think of it like three people carrying a really heavy piece of furniture. But what happens if one phase is lost? Maybe a wire gets disconnected somewhere down the line. Well, the motor doesn't just politely turn off. No, it frantically tries to keep running on just those remaining two phases. And when this happens, that massive electrical current that was supposed to travel through the missing phase, it doesn't just vanish into thin air. It gets shoved entirely into the remaining two phases. This forces a massive, rapid spike in the winding temperature inside the motor. If your protection system isn't monitoring for this specific imbalance and fails to act in time, well, that motor is absolutely guaranteed to burn out. And the crazy part? The overall panel might look totally fine from the outside.
Moving right along to suspect number 2, human negligence, the casual approach.
Picture this, completely terrifying but super common cycle on the factory floor. A single phasing event happens, the current spikes, and boom, the relay trips to protect the motor. Exactly what it's supposed to do, right? Great. But then, an engineer walks by, sees the tripped relay, assumes it was just a random hiccup, and casually smacks the reset button. They just give the start command again without actually checking if all three phases are, physically there. So the motor tries to start on that exact same active fault, it violently trips again, and the engineer hits reset again. Actually, it's basically like hitting snooze on a fire alarm. Blindly forcing start commands 2 or 3 times without stopping to diagnose why it tripped in the first place, that is a 100% guaranteed recipe for a burnt-out motor. The electrical protection worked perfectly, but the human completely bypassed it.
But hey, even if nobody is actively standing there mashing the reset button, passive errors can be just as deadly. You see, overload relays have these little adjustable settings and ranges. If the relay's capacity setting doesn't accurately match the specific motor's actual capacity, it's essentially useless. It's asleep on the job. So when that current dramatically shifts during a single phasing event, an incorrectly set relay won't even realize there's a problem right in front of its face. It'll just blindly allow that excessive, dangerous current to flow right on through. And once again, you're left holding a burnt motor while the relay just sits there, completely untripped, thinking everything is fine.
Which brings us to suspect number 3, incorrect protections. Literally the wrong line of defense.
So you kind of have to ask yourself, are we expecting the overload relay to do a job it literally wasn't hired for? An overload relay is specifically designed to protect against overcurrent or a mechanical overload. We're talking about a slow, steady increase in heat over time. But what if your motor suffers an earth fault or a massive short circuit? Those events aren't slow. They create an instantaneous explosive spike in current. An overload relay simply cannot react fast enough to handle that. For short circuits and earth faults, you have to rely on MCCBs, that's molded case circuit breakers or HRC fuses. They are your extremely fast, specialized line of defense for those high-magnitude, instantaneous faults.
Let's put this into perspective and look at the real-world consequences of getting this wrong. Say an earth fault happens. The current magnitude just goes absolutely through the roof in a millisecond. Now, if someone installed an incorrectly rated, massively oversized fuse for a relatively small motor, which happens all the time, by the way, what do you think happens? That massive fault current hits like a freight train, but because the fuse rating is way too high, the fuse doesn't blow, it doesn't melt. It stays completely intact. So all that destructive energy travels straight past it and right into the motor, absolutely destroying it. Later on, some poor engineer is going to open the panel, see a perfectly intact fuse, an untripped relay, and a completely roasted motor. This right here is why proper rating selection across every single protective device is absolutely crucial.
And finally, our last culprit, suspect number 4, poor ventilation or suffocation by dust.
Look, motors generate a ton of heat, and they physically need to breathe to stay alive. Most three-phase induction motors have these cooling slots and a fan at the back, specifically designed to constantly draw fresh air over the unit. But out there in a harsh industrial environment, a motor might literally get buried under inches of thick industrial dust. Or maybe falling raw materials completely bury the unit, totally choking off those ventilation slots and the cooling fan. In this scenario, your entire electrical system could be 100% healthy. The relay settings are flawless, the fuses are perfectly sized. But because the motor is physically suffocating, the internal temperature just steadily rises and rises until the internal windings literally melt together. It's crazy, but your highly advanced electrical relays cannot save a motor from basic environmental suffocation.
So, bringing all the clues together for the final verdict, engineering responsibility.
We've looked at the silent killer of single phasing, casual human negligence, mismatched protection ratings, and physical suffocation. And it really all boils down to this. It's not just about having a healthy system on paper, but how seriously you identify symptoms in the real world. Having an overload relay installed in your panel? That is just the bare minimum. True engineering responsibility lies in how you actually interact with that system. If a relay trips, it isn't just an annoyance, it is the machine screaming at you that there is a symptom of a much larger disease. Identifying that symptom with actual seriousness, rather than just throwing a switch and crossing your fingers, is the true mark of a reliable professional.
So, I'll leave you with this. The next time a relay trips out there on your factory floor, will you take the casual approach and just blindly press reset? Or will you pause, do the detective work, investigate the root cause, and actually protect your equipment? Thanks so much for joining me on this explainer. Stay curious, stay observant out there, and I will catch you in the next one.